Okay. Here's our quiz. And the process is pretty straightforward. There's some details. Okay, so again, really want to be writing these out carefully on the way you've seen me write them out. Or the way you see it written out in math, open math. You want to write all the details so you retain them. Because test is due a week from yesterday. Okay. And this could be on the test. Everybody gets a set of problems I sent out a couple of days ago. And would make sure I can do all those problems. And practice. Know how to write them out. So if you know how to write them out, you know what to write, you're going to remember what to do. Okay? And practice is the key. Everybody can do this. It's a question of finding the time to practice what you need to do. Okay. And everybody got a copy of their test with the annotations and stuff? You know how to use that? Open it in Adobe. And then you can click on the little comments and expand. Okay. Okay. And I recommend you do take a close look at my comments. Okay. So x equals 2 is a 0. P of 2 equals 0. So P is divisible by x minus 2. Means x minus 2 is going to be a factor. X minus 2 is a factor. That's why x equals 2 is a 0. Okay. So we have to do the long division. We write out the long division. Goes into x cubed, x squared times. Remember, you can always ask yourself, what would I multiply by this to get this? That's what you get when you divide this by this. Okay, then you multiply x squared by x, you get x cubed. You multiply x squared by minus 2, you get minus 2x squared. And then what do? Well, I've explained, and you know, this is a little hard to understand. You're not required to understand it, but if you do, it makes a lot more sense out of it. You know you're going to need an x squared. Because x squared times x is going to give you your x cubed. Turns out that x squared multiplied by the minus 2 is going to give you your minus 2x squared. So by having x squared here, if this is a factor, this times x squared gives you this much of your polynomial. Okay, so still, I recommend you write it down with a minus here and a plus here. Another thing I've seen, open math apparently told you, just put a minus in front of this, put parentheses around it. Remind yourself that you're subtracting it. And if you get that, that works all right too. But in any case, if we change these signs and add these things, we get 0. And we get 0. Okay, so we've already got x cubed minus 2x squared. Next thing we need is a 3x. So, you know, officially we'll bring down the 3x. And we'll actually bring down the 3x minus 6. Okay, and these zeros don't have to be there. I'm just going to put a double underline here, indicate that these are identical. We're going to get 0. Now we've got to divide x into 3. 3x, we're going to get plus 3. So now we have 3x minus 6. And this is identical to this. We're going to be subtracting this. We've got it. Okay, now check. X minus 2 multiplied by x squared plus 3 is x times x squared plus 3 minus 2 times x squared plus 3. Give us x cubed plus 3x. And then it's going to give us negative 2x squared minus 6. Then putting these terms into order of decreasing power, we say that x minus 2 times x squared plus 3 is equal to this. Okay? So, here are zeros. Solutions to the equation P of x equals 0. P of x is x minus 2 times x squared plus 3. That's 0 if x minus 2 equals 0, or squared plus 3 equals 0. There's a reason I want you to write this out. Like, okay, until it becomes very clear to you why you do this. Okay? You write a narrative and you remember it better, and eventually you understand it better and better. Okay, so let's see, we've got x minus 2 equals 0, or squared plus 3 equals 0. Okay, well, x minus 2 equals 0 obviously gives us x equals 2. How do we solve x squared plus 3 equals 0? Well, we can subtract 3 from both sides. We get x squared equals negative 3. Okay? And then if we know that the solution of this is x equals plus or minus the square root of negative 3, we see that our zeros do x equals plus the square root of negative 3, x equals minus the square root of negative 3. But that's not minus or minus. This minus is under the radical. You don't say minus and minus gives you plus. That's not what you have. Okay. You say, okay, well, yeah. But we're solving over the complex numbers. This means that x equals square root of 3, or x equals negative square root of 3 times off. Okay. That should be very clear. Now, some of you might have gone ahead and used the quadratic formula on this equation, and you would have ended up with the same thing. Okay. When you divide a linear term into a cubic polynomial, you're going to get quadratic. Okay. That quadratic might have two real solutions. Okay. It might have one repeated real solution. It might have two complex conjugate solutions. Okay. So this is how we factor this polynomial and then determine its zeros. Now, these zeros don't contribute to your graph. I mean, they do, they have an effect, but they aren't going to be points on the x-axis because these aren't real numbers, and the x-axis only contains real numbers. So you don't know where these things are. They're out there in the ozone somewhere. Okay, as far as you know at this point, there's a lot to this, and we don't go much deeper than what I'm just saying here. So now we know if we're to graph this POX, the only x-intercept we have is a 2, 0. The y-intercept occurs when x equals 0. P of 0 equals -6. This is 0, this is 0, this is 0. You're left with the -6. Okay, so we have the line y equals -6. We have a 0 on that line. And then we have the long run behavior. In factored form, if x is a large positive number, then this is positive, and well, this is positive no matter what x is, isn't it? X squared is always never negative, okay? And when you add 3 to something that's never negative, you get something that's positive, right? So x squared plus 3 is always positive. This is negative when x is a big positive number. So your long run behavior. And write this out the way I've been writing it out. I'm not going to write out all the details again because there's other things we need to talk about. But the long run behavior as x goes to infinity, p of x approaches infinity. If x is a large negative number, then this is a large negative number. And this is positive, and when you multiply negative by positive, you get a negative. Since this is big and this is big, you get a really big negative number. So graph is down here. And that's about all you know. So what's going to happen is the graph is going to come up from here. It'll come up pretty steeply. It's probably going to level off a little bit. Then it's going to go back up. Pretty boring looking graph. That would be the process of graphing this function. Okay. Now, I'm going to switch gears and I'm going to introduce the idea of rational functions, which are very much like polynomials, but they're different. Okay. But everything we've done with polynomials helps us understand rational. Okay. So here's an example of a rational function. What you see is it's like a fraction. You got a polynomial up here and a polynomial down here. That's what a rational function is. Polynomial divided by polynomial. Okay. Now to explain the way the graph works here, I'm going to write this Okay. Everybody agree that this is the same as this? I'm gonna say that, okay. Mark off our zeros, one at x equals 3, and one at x equals -6. And then we're gonna also mark off x equals, I'm sorry, should have done x equals 6 as one of the zeros. Okay. X plus 6 is 0 when x is -6. And x minus 2 is 0 when x equals 2. So we're going to mark those off too. And we're going to mark every point that makes any one of these 0. And then we're going to figure out what to do with it. Okay. Well, if x plus 3 is 0, that makes the whole thing 0, doesn't it? Because if this is 0, well, then this times this is 0. And whatever we have down here, unless it's also 0, it's still going to give us 0. So that x equals 3 is going to give us an x-intercept. Also, if x equals 6, that makes the numerator 0. And it's going to multiply the rest of the numerator to give us 0. And when you divide something that isn't 0 into something that is, again, you get 0. So we're going to go through the x-axis here. Those are our x-intercepts. Now, I did something really big right there. I said x equals 3 was a 0. Now I was just kidding you to see if you're paying attention. Okay. X equals -3 is a 0. So if you write everything out completely, you would write x equals 3, 0. X plus 3, anyhow. Okay. The x plus 3 factor makes it 0 when x is negative, not when x is. Okay. Now, what do we do with these zeros that we got from the denominator? Well, what does the graph of 1 over x plus 6 look like? Well, it's a reciprocal function, shifted 6 units to the right. Okay. So let's observe. One over x minus 6 is a reciprocal function, shifted 6 units horizontally, which would give us something might look like this. With an asymptote here, right? Okay. And that function is multiplied by what? Multiplied by this times this times this. Well, if x is close to 6, if that is true, obviously, I'm not totally alert today for some reason. It's 1 over x minus 6 is the reciprocal function, shifted 6 units horizontally, which would come over and look like this. Of course, we don't have 1 over x minus 6. We have 1 over x plus 6, right? So x plus 6 is shifted -6 units horizontally. So that might be over here. Okay, it might. For that reason, well, if x equals -6, x plus 3 is -3, x minus 6 is -12. Okay, so -3 times -12 is 36. And x minus 2 is 1/8. So we get 8/36. Okay. Which is a little less than 1/4, or a little less than 4.5. Okay. Now my point is, if x equals -6, right here, this times this times this is equal to what? Again, this is negative, this is negative, and this is negative. It's going to give us -4.5. Okay. If we multiply the reciprocal function, shifted reciprocal function, 1 over x plus 6 by -4.5, it's going to look like this, except for multiplying it by negative. So everything flips around the x-axis. It'll do something like this. Okay. Now that's only when we're close to x equals -6. It's not going to apply over here. But what that's going to leave us is it's going to leave us a vertical asymptote. It probably looks something like this. That's just the steep part of the 1 over x minus 6 graph. So we kind of draw -4.5 times 1 over x plus 6. That's about what this function is going to be at this point. Now, I'm not going to, except for an optional problem, maybe even a little extra credit, I'm not going to ask you what the specific function is here. I explain this so you understand that this 1 over x plus 6 just takes the reciprocal function, which has a red dot here, shifts it over 6 units here, and multiplies it by whatever these things give. And whatever this times this is, at x equals 6. And for values very close to x equals -6, it's going to follow this function. So we're going to have a vertical asymptote that looks something like this. Okay. Similarly, at x equals 2, we're going to also have a vertical asymptote. Now we could plug in x equals 2 here, here, and here, and see that, again, we're going to get a negative, so we can figure out where the vertical asymptote is. Right now, all we're going to do is we're going to make this line a little more solid. We're going to make this line a little more solid. Say we got vertical asymptotes here and here. Like the reciprocal function. Okay, because this is a shifted reciprocal function, this is a shifted reciprocal function. Okay. Now this is a linear function and this is a linear function. So we know we go through this 0 and this 0 linearly. So everything's linear or just plain old reciprocal. Any of that make sense? This tells us that we go through here either this way or this way. This factor tells us we go through the 0.60 either this way or this way. This factor tells us we have a vertical asymptote that has the behavior similar to a stretch on a reciprocal graph, because this is just a shifted reciprocal graph. And the other numbers we get from these other factors tell us what the stretch is. Okay. Same thing here. If we understand that, then it isn't too difficult to sketch a graph of this function, but we still have to consider the behavior as x approaches infinity. Okay. Now imagine that x is 1,000. Okay, that's a number. It's way out there, and it's out there. You know, you can get a lot bigger than 1,000, but if x is 1,000, then what do you get for x plus 3 times x minus 6 over x plus 6 times x minus 2? Well, 1,003 is pretty close to 1,000, right? Okay. If somebody says, I'm going to give you either $1,000 or $1,003, are you going to lose any sleep over that $3, whether you get that $3 or not? Yeah, you're going to want that $1,000. And if it's 1,003, it's just about the same thing as 1,000, right? It's an extra $3. You can buy an ice cream cone with it or something. Okay. And x minus 6. Well, that's 994. Okay. 994 or $1,000. Okay. If you do 50 push-ups, I'll give you the 1,000. Otherwise, I'm going to flip a coin. Are you going to do the 50 push-ups? Well, most people can't do 50 push-ups, so maybe just say, it's okay, 994 is close enough to 1,000. If I get to 994, it's not going to make a big difference, right? That makes sense. Okay, well, you can say the same thing about these. This is about 1,000, this is about 1,000, this is about 1,000, this is about 1,000, right? So what do you get when you divide 1,000 times 1,000 by 1,000 times 1,000? Show me with your fingers. 1. You're essentially dividing the same number by the same number. So a little bit of difference, like that 994 and 1,000 or 1,000 to 1,003, right? It's not going to be exactly 1, but if you put that into a calculator, it's probably going to give you 0.99 something. Okay? Real close to 1 or 1.0 something. So the long run behavior, I'll just say if the absolute value of x is very large, I'll say none of these differ significantly. So the numerator and the denominator don't differ significantly. So when you divide these, it's going to be close to 1. Okay? So we get something here that you don't see with polynomial. In this case, y equals 1 is a horizontal asymptote. I can't read that. I didn't spell it all out, but it's a horizontal asymptote. This means that if you go way over here to the left, the value of the function is either a little bit more or a little less than 1. Okay? Now, If it's a little less than one, then when you come over here and approach this asymptote, you're gonna go down. And that doesn't work. If it's a little more than one, you just come over here. Approach this line just kind of like a 1/x, right? With a negative stretch. Then you can come over here and you got to go on the other side because it's like 1/x. And 1/x, you've constructed many times, gives you two little curves on that approach the y-axis on opposite sides. So you're going to come up from here. You know, the one thing I didn't do is I didn't specify the y-intercept. That occurs when x equals 0. So y equals r of 0, which is 0 plus 3 times 0 minus 6 divided by 0 plus 6 times 0 minus 2. That's negative 18 over negative 12. That's 3/2. So here we have line y equals 3/2, and there's our y-intercept. So now it makes sense. We come up from down here. We come up and we law. But then we go back up like this and approach this y-intercept. Because remember, this is like both of these vertical asymptotes are like reciprocal x functions. Okay. That means that on the other side of the asymptote, we're going to come up through here. And we're going to go through this 0. Come out here and just kind of level off because we're going to approach this y equals 1 asymptote. Okay. As x goes to infinity, we've got to just approach this line y equals 1. Does that have to make sense? It's a whole lot like what we do in polynomials, and we find the zeros, but we also find the zeros of the denominator, and those zeros give us the vertical asymptotes. Most of the time, there are exceptions, but the math won't explain. Okay. I'll do example 2. Okay, now this is a polynomial over polynomial. This polynomial can just be linear factor. And it should be clear that the zeros -7 and -3. And the denominator has just 1 0, that's at x equals 2. So let's put x equals 2 here. And that's a 0, the denominator, so it's an asymptote. I snuck the word vertical in there. You probably can't read it from where you are, although it is semi-readable. Vertical asymptote like 1 over x, except I lied. Functions x minus 2 squared, just to give us a little variety. So now the vertical asymptote is like 1 over x squared. What I mean by like 1 over x squared, I mean close, very close to this x equals 2 line. Thing behaves like a vertically stretched reciprocal square. Okay. And the vertical stretch is just, well, 2 plus 7 times 2 plus 3 is 45. Okay. So that is stretched out reciprocal square. And it's going to be kind of like this, right? And let's see if that makes sense. I do that very lightly because by the time I sketch the rest of the graph, the curve probably won't follow. Okay. Now you also have the zeros at x equals -3. You have a 0. And at x equals -7. You have a 0. So you have x-intercepts at -3 and -7. Okay. Now, long run, as x goes to infinity, end behavior. Large positive x. X plus 7 times x plus 3 over x plus 2 squared. And let me write that as x plus x minus 2 times x minus 2. You see, again, we have a situation like we had before. If x is 1,000, then it's about 1,000 times 1,000 over 1,000 times 1,000, right? And if x is -1,000, well, it's -1,000 times -1,000 divided by -1,000 times -1,000. The numerator is still pretty close to being the same as the denominator. So again, we have, I'll do this. Y equals 1 to horizontal axis. Probably should have made y equals 1 lower because the y-intercept you get r of 0, which is 5 1/5, a little over 5. So that means my y-intercept has to be quite a bit higher than I left myself room for. I'm going to fudge a little bit. I can fudge my scale, but I don't like to do that. I'm just going to make my horizontal axis a little lower so that my y-intercept is about 5 times that high. It's 0, 21/5. I said 5, it's 4. No, it's 21/4. It's 5 1/4. About that. Okay. So how do we draw the graph? Well, up over here, gotta go up over here. It does that by coming down through this 0 here, going over and approaching this equals -3 line. Oh, sorry, that's not an answer. Okay. Come down through here. And on towards this vertical asymptote here. That makes sense? It's got to approach this x=2 line. Right? Then on the other side of that line, it comes back down because it's like a 1/x² function. Because a 1/x, it would have to come down here and come back up and approach this horizontal asymptote, but it can't go through the x-axis because there's no 0 there, right? So you don't try to draw it from here. Just draw it from here. It comes down like this. And I'm just clicking my brain. Let's do this. It's got to approach the horizontal asymptote. So it comes over here from the horizontal asymptote, goes down through the 0, then back up through here, and then it does what I said. Then it comes down from the vertical asymptote, comes over here, and approaches the horizontal asymptote. I have no idea why I did this and this. Okay. But it's not consistent with everything else that I did. Idea? These things give you zeros, vectors in the numerator, okay? Just like polynomials. And they'll behave like you do with polynomials. That is, if this had multiplicity 2, then it would look like a parabola near the 0. Okay. Then the factors in the denominator are basically giving you reciprocal or reciprocal square, reciprocal cube type functions. Give you vertical asymptotes. Do one more and let me make sure I check. R of x equals, let's say, we need to keep this one. Then when x equals -1, we have a 0 here, and it's got multiplicity 2. make that x plus one, so I'm telling the truth. Instead, I was gonna try to do it right, and then I did a bonehead thing like that. And I'll go ahead with an x minus 3 over here. X equals 3. I've got a 0, an x-intercept, a multiplicity. Then at x equals 5, asymptotes. I'm going to make that kind of a light vertical line. I'll say like 1 over x. My intercept is when x equals 0. So y equals r of 0, which is going to be negative 27 over negative 8. About 3 1/8. So I'm going to say, okay, we're going to put that here. Now, as x approaches infinity, it should be clear that x plus 1, x minus 3, and x minus 5 are all going to be positive. It should be clear that the numerator, which has 5 factors, if you count multiplicities, it's going to have a product of 5 really big numbers divided by just one really big number, which means it's going to get really huge. That makes sense? And if you don't believe me, plug in x equals 1,000 and see what you get until you develop a number sense to that. So here's my long-term behavior on the right. I'm not going to write it all out, but you should. Okay. Now, if x is a big negative number, what do we have? We have a product of 5 negative numbers here, right? Now, it's 5 negative numbers. Does that give you a positive or a negative? You multiply 5 negative numbers. Positive or negative? You get that quickly? That should be quick and automatic, okay? An odd number of negative numbers is always going to give you a negative, because negative times negative is positive, times negative is negative. Okay, so 3 negatives gives you negative, 2 negatives gives you positive, right? A fourth negative makes it positive again. So it turns out if you have an even number of negative numbers, you're going to get a positive, whether you're multiplying or dividing. Okay. If you have an odd number of negative numbers, you're going to have a negative. Okay, well, if x is a big negative number, then all these are negative, and you got 5 negative numbers up here divided by a negative number here, right? So that's 6 negative numbers being multiplied and divided. That's going to be positive. You sure you understand that? You can't figure out the long run behavior. Or what's wrong with this? I come down through this 0. Oh, this 0 has multiplicity too, doesn't it? So if I come down through this zero, then I can't get back up to this y-intercept. So it's a good thing I looked at this factor and it might note that the multiplicity is 2, right? That's why you make these little notes. Even if your brain isn't completely working on a certain day, you can figure it out. Okay, so it's going to come down like this. It's going to go back up. It's going to go through here. Then it's got to turn around and have a 0 here, and the 0 has multiplicity 3. Well, that means it's going to behave like the cubic function. We're going to do this. And then it's going to come down and approach this asymptote. Unfortunately, this asymptote is like the reciprocal function. On the other side, it's going to come down from up here. And now how's it going to get back up? Well, it's going to turn around and it's going to go back up. It's allowed to do that. Okay? Well, those are examples. Open Math will give you more examples. I wanted to get you started on this today. Now, the schedule for the assignment, this won't be due until Monday night. Giving you the rest of the week to review, and we'll do some review on Thursday. I'll probably let you work a little bit. Because what you really need to do is you need to get into those problems that I sent out. And I'm going to send you out something else that I thought I'd already done. You'll see it on the website. I'm going to look again. And I really intended you have that for the major quiz. It's just a set of algorithms. Here's how you do this. Here's how you do this. Here's how you do this step by step. It's not complete. It doesn't tell you how to do everything. And it doesn't address polynomials. But I'll try to expand a little bit. Okay. I'll give you step-by-step directions. If you can follow those step-by-step directions, then it should give you enough to at least make a decent grade. At least see. Hopefully it'll be if you looked at that a little more and put it together. Okay. So you can use that as a guide. You can use the problems I sent out as a guide. The test is pretty predictable. There are less than 30 problems. The numbers will be different. Sometimes the words will be a little different, but they're really less than 30 things that I'm going to select a test from. And I've already got the test in the testing center. I don't remember how many problems are on. It's 8 or 9. In those 30. I think it's 9. It's give or take 1, that's what it is. Okay. So if you got questions, email them to me. Come and find me during office hours, whatever. Okay. And give the best response I can. Also, that last assignment on polynomials, I extended it, but I didn't extend it that day. Somebody emailed me the next day and says, hey, I can't do this. So I extended it, but nobody did it. So I'm going to extend that also to Monday. But be sure you do that one because that stuff's going to be in the test. Does that make sense? Okay. Okay. Stick around and ask.